intersection of two planes. All right, so you're coming towards the end, okay, with regards to these vectors and understanding lines, planes in 3 dimensions. And maybe you're running into this problem of trying to figure out what happens when you have 2 planes and how can they intersect, or can they intersect at all. So it turns out that there's really just 3 possibilities if you take 2 planes and you can visualize them. So I have done that for you through plotting it out, okay, on a software tool. And within here, so what you notice, if you take 2 planes, right, so we're of course assuming that they're infinite planes. One thing that can happen is that the planes themselves can intersect at a particular line. So you're never going to get 2 planes intersecting at one point. You would need at least 3 planes, right? But if you have 2 planes, you can certainly have them intersecting in a line, especially when they are infinite planes. So within here, so as you can see, I can draw out, I can zoom in on the first one in here. So I have a plane which is kind of red, and then I have a green plane which cuts right through it, and then you notice that they are intersecting. Now of course this is going to be an infinite line, right, in terms of going on into infinity. So I got to be careful here. I'm going to make it a little bit smaller. All right, so within there, so if I go in there, okay, so this is going to be a line which is going to be intersecting, right? That's going to be the intersection of the 2 planes. Now, you of course can also run into the problem where you can have 2 planes that are parallel to each other. And this one is actually not very difficult to be able to spot, because you can look at the normal of the planes and they're going to be scalar multiples of each other. And if you do have the planes in scalar form or in standard form, so the ax plus by plus cz plus d is equal to 0, or that form in general, then you can just look at the actual normals, okay, and then compare and then see what happens. The third thing that can happen is, of course, the planes are actually identical. They're just lying right on top of each other. So I tried to put one plane on top of each other. You can maybe see there, okay, they're kind of hovering over each other right there, but really they're just the same exact plane. And for that, you know, their actual standard equation of the plane will be the same. It might be just a scaled version of each other. So those are really the only 3 things that can happen. Now, the question, of course, might be, is in particular of the line intersection, like how could we possibly find that line that intersects, right? So that's not always the easiest thing unless somebody shows you how to do that. And you may run into this, okay, either your teacher showing you this, you might see it in textbooks, okay, or maybe you're watching it as a video like this. So let's take a look at some examples. I try to create an example for each of these cases, okay, when the planes are intersecting. So here it is. Here's our first example. And notice what I wrote here. I wrote here systems of linear equations. Now I put in 3D because planes are going to be 3-dimensional. But this concept of systems of linear equations, you have done, and you've done a lot of this, except you did it in 2 dimensions. And if you recall, so this was the case if you go back to 2 dimensions and you start working in 2-dimensional systems. So it was really, you know, if you had 2 lines and you would write that outline. So here's one example, for instance. And you would have these 2 particular lines. We called this a system because it was a grouping of 2 lines. And then we were asking the questions, how do they intersect? Now, of course, for lines, they could intersect at a point, right? So they could not intersect at all, right? So they could be parallel lines, okay? Or they could be lines that are lying on top of each other. Well, déjà vu. This is exactly the same thing that happens here, except we don't have 2 planes intersecting at a point. They intersect at a line. But the other 2, so being parallel and being right on top of each other, is the same thing we ran into these systems. Now, how did we solve these? Well, we basically solved these either through the elimination method. So that was one of the methods that you could have solved it, or by isolating, okay, and substituting. So that is definitely two ways that you can do this. Now, with only two variables, okay, it was rather easy. Now we have three variables, but that's not going to be any different. Now, if you wanted to review this concept, okay, in terms of elimination, and you're probably going to date yourself back to grade 9 and grade 10, but maybe you haven't done it since. It is worthwhile to know what this process is, because the coefficients could be anything. Of course, they could be decimals, they could be fractions, right? So whatever that might be. I'll put up a link up above there for you in case you've forgotten about, taking two lines. We called it a system of linear equations because they're linear, they're just lines. Now, we are also dealing with linear equations, except they're no longer lines, they're planes. But if you think about a plane, it's still linear because it's a combination, right? If you think about in terms of the vectors that create that line that can lie on top of that particular plane. So now, how would we solve this using the same thing? So I love, especially as you go into 3D, now this can also extend to 4D, 5D. Now, of course, we can no longer visualize what the heck that means in 4 dimensions, 5 dimensions, and so on. But in 3 dimensions, we still can, and we know that these are planes. So I've given you two planes. I have given you one plane, and I've given you another plane. Now, I've put them kind of in standard form, okay, or at least some version of it. At least the first one is in very standard form, and the second one, depending on which teacher's teaching it, that might still be considered the standard form or the scalar form. And now the question is, all right, how do these intersect? Do they intersect? And what should I do? So what you should do is you should use the process of elimination or substitution, okay, as you're going through. So now, what did we mean by eliminate? Well, we wanted to eliminate one of the variables, right? So we wanted to make it smaller. So we were trying to solve, okay, until we get something, and we finally solve for a variable. Now, we only have two equations, but we have three unknowns. So we're not going to be able to solve this because it's not going to have a solution for a point. The best we could do is we could possibly solve it for a line. But we'll get there, all right? So let's see how this, okay, turns out for us. So we have two planes. Now, you can just eliminate any of them that you like. So I can spot the coefficients. So I'm going to look at 2, 5. This is a 1, 2.5. Right, -2 and -5. So I can eliminate any of them. I'm going to actually eliminate y, or I'm going to try to eliminate y, because this is 1 right there, and the other one is 2.5. So I'm going to multiply this by 2.5, right? So I'm going to multiply that entire equation. It doesn't change it. It just scales it. So what that would give me is, so if I would do that, that's going to give me, I guess, 5x plus 2.5y minus 5z, and this is going to be 2.5 times, so that's what, 6, that's 7.5, I guess, so that's plus 7.5 equals to 0. Now, I'm going to move this over, this one, actually, so that's 7.5, I'm going to shift over, so it's going to become negative. And then my other one, notice I'm just going to rewrite 5x plus 2.5y minus 5z is equal to 1. And look what you can see there. So this right here, sure, I wanted to eliminate y, so that's why I multiplied by 2.5. But as a result, if I take these two, and now I'm going to subtract to try to get rid of that y, well, I'm not going to just get rid of that y. Notice 5x minus 5x, so that's 0, and so that's going to be 0x. The 2.5 and the 2.5, that also cancels, and the -5 minus -5 also is gone. So this is actually going to be 0, equal to, and this is going to be -8.5. Well, clearly you can see here, from trying this process of elimination, I am running into 0, trying to be equal to -8.5, which is never true. Now, what does this mean? This means that there was no solution. This was the same thing if you were working out with just two unknowns, right? So if you came in and you noticed that this was 0 and then some number n, right? So these were never equal. So that meant that there was no solution. Well, that's the same thing that happens here. Now, what is the only instant when two planes in 3 dimensions have no solution? Well, what that means is these are going to be parallel to each other, right? Now, also notice when I tried and I multiplied this by 2.5, so when I multiply this by 2.5, this is what I got. And what you should notice is that right away, notice what I have created is I've actually created the fact that they have exactly the same normal. So your A, your B, and your C are the same, which means that the two planes are definitely parallel. And the only thing that you really needed to check was this. If these were the same, then the lines are identical. They're lying on top of each other. If they're different, then there's clearly not going to be a solution, and that means the planes themselves are going to be parallel, okay, but distinct, okay? So they're going to be different like we saw there in the picture. So that is one example. Here's another example, okay, so that I have for you. So let's give this one a try. So within here, I'm just kind of scanning. So again, I'm going to try to eliminate one of the variables just to see what happens. This one, okay, so I like to always pick wherever there's a 1 if I could. So here's a 1, and then notice here's a 3. So I can actually multiply. So if I wanted to get rid of this, I'm going to multiply this by 3. This one by 3. So this is my plane 1 and my plane number 2. Now, what is this going to give me? So if I try to do that, that's going to give me 2.1x minus 0.3y minus 3z. I'm going to shift that over. So it's going to be 12, but it's going to be minus 12 right there. I think that's what I see there. So that's going to be, yep. So it looks like that's what I have right there if I multiplied by that. Now, my second one right here, so that's going to be negative 2.1x. All right, so this is what I have there. And now this is going to be plus 0.3y. And then this one is going to be plus 3z. I'm going to shift this other one over as well. So that's going to be 12. All right, so now I have my two actual planes. And now, because I have, so I was trying to get rid of this. So I would be adding these two up. So I would be adding these two in so that those z's or z's cancel. Now, but if I add it, notice I'm going to run into the same problem. So this is going to be 0. This added plus this is 0. And then this is going to be 0 as well. So this is just 0 on the left-hand side. And then notice, adding the right-hand side, I also get 0. This is always true. This is always true. So what does this mean? This means that we have infinite number of solutions. And really what it means is that we're running into this problem. The lines are identical, all right? So I could see this actually even from the fact of multiplying it by 3. So sure, you know, I got 2.1 instead of negative 2.1. But if I really wanted to, you know, I could have, again, multiplied this by negative 1, and I would have gotten the same line back. And if you get the same thing back, it just means those are two lines that are parallel and they're on top of each other. So that's it. That's how you would be able to solve this one. So that process of elimination is pretty neat, but you can also look at the normals and then conclude from there, all right, what happens to those planes. Here's a third example and our last one. Now this one, I think I set it up so that it hopefully doesn't cancel for us. So let's try it. I'm going to try the same thing here. So I have two planes, right, and I'm going to try to begin this out. Okay, so I'm going to just try to see what happens here. So this is a 1. Okay, and then this is a 2. I'm going to multiply this by 2. Let this be 1, let this be 2. So if I do that, I'm going to get 2x minus 2y plus 4z. I'm going to shift that over, so it's going to be 2, but it's going to be negative 2. And then the bottom one, so it's going to be 2x plus 3y. There's no z. I'm going to put 0, z. And then I'm going to shift this one, so that's going to be that. So now by the process of, again, of elimination, I'm going to subtract them so that I get rid of this x. So that's gone. So this is going to be giving me negative 5y and plus 4z is equal to, and this is negative 7. All right, so this is what I have. And now notice we don't have the case where we have 0 on the left-hand side and a number on the right-hand side. So they're not parallel in any way, right? Now, I could have also seen that from the fact of trying to look at the normal. So notice that my first normal right there was 1, negative 1, 2. My second normal right there was 2, 3, and 0. So now what do we do? Because, we don't have any other further equations. If we had another plane, so if we had a third plane, then we can continue the process of elimination and then maybe eliminate another variable and continue and so on. But here, this is as far as we can go. And so what this tells us, right, if you do the elimination of one and you still get something back like this, then that means that they intersect at a line. But this is not an equation of a line. We can't say negative 5y plus 4z is equal to negative 7. So that would have been an equation of a line if we only worked in the y and the z, right, coordinate system. So that would have been okay. But we're not. We're working in 3 dimensions. So how do we do it? Now recall that in order to get an equation of a line, there is no standard equation in 3D. There is no, slope y-intercept. There really is only either vector or a parametric equation, right? So we have to try to find some equation which looks like this. So it's going to be looking at something like this where the parameter is t, and then we have some vectors. So notice, so this is my vector which is going to be touching the line, and this particular vector is actually a vector which is parallel to the line. So how do you do that? There's actually 2 ways. Now most of the time in textbooks or through teachers, what you're going to do is, it's probably the easiest way, you're going to right away use the parameter right here arbitrarily, okay, to set it, and then just go back to fill in your line. So that's going to be one way. So I'm going to just show you what this way is. Okay, so this is way this is the first way to be able to do that. I'm going to split this kind of screen in half. So the first way is to say, okay, I came to this point. So I have this, right? And so I'm going to duplicate it and bring it back down. And now I'm going to just arbitrarily set, right? So I'm going to just arbitrarily set the variable because I need to have it in this format, right? So something like this. I'm going to try to find this out. So either this or in the parametric. So here it is in the parametric form. Currently, I have a y and I have a z, right? So what I'm going to do is I'm going to pick one of them. It doesn't matter which one at this point. So let me just say, all right, I'm going to let y is equal to t. So notice the t is just my parameter of choice that I'm going to have. Now, if I have that, if I know that y is equal to t, I can now substitute it back in. So I'm going to get negative 5t plus 4z is equal to negative 7. Now, this is a parameter, okay, of the line that I'm trying to find. So now what I'm going to do is I'm going to try to isolate for z. So I'm going to have what z would be in terms of t. Okay, so 4z is equal to, I'm going to shift it over, so negative 7 plus 5t. And now dividing by 4, I'm going to get that z is equal to negative 7 over 4 plus 5 over 4t. So now I have two things. I have a parameter-based y, so I let y is equal to t, and I have a parameter-based z, which is equal to negative 7 over 4 plus 5 over 4t. So I've now found two. I found my z and I found my y. Well, now you can probably deduce that I can now take my y, so I can take this y, I can take my z with respect to the t that I've already set, and I can substitute it back into one of the equations that I started with. Now, it doesn't matter which one I go with, equation 1 or equation 2. So, I can, for instance, plug it into here, so my y and my z, and then I can solve for my x. So that's exactly what I'm going to do. So I'm going to bring one of these. So I'm going to copy it. Okay, so let me bring it down and paste it. And now it's going to be a little bit of work. I mean, it's annoying, but that's fine. Now my y, that one is easy, so that's just t, plus 2. My z is not so easy, so 7 over 4 plus 5 over 4t, okay, plus 1 is equal to 0. And now I have to be able to isolate for this x. And I can now get x in terms of the variable t. All right, so what will I get? So I'm going to just massage this in fast forward fashion for you. So let me just do it in quick form. All right, so welcome back. So here it is. I mean, I just kind of massaged it out. So basically just isolated for x. And this is exactly what I have found. Okay, so within here. Now, once you have that, you can certainly get your parametric equation of the line. So that would be it. And if you want to transform it into its vector equation, okay, so that will be right there. So that is it. That's all that you would actually have to do. And now this is just one way of finding it. Now I said that there's two ways. Now the other way, please remember that when you have two planes and they're intersecting at a line, so once you know that they're intersecting at a line, what you really need is, right? So what we need, if you're looking at this, you need a vector, right, which is going to be parallel to this actual line, right? So you need a vector which is parallel. And we typically call this, vector M. Now, your teachers might call it something different. In the textbooks you use, you might be something different. But you definitely need a vector which is parallel to this, right? And you also need another vector, right, which is starting from the origin, okay? And that origin, and now in this case, it's that origin is stuck all the way behind there. But you would need a vector that actually, I'm going to just kind of shift this just so that it kind of looks like a vector. But this would have been coming from the origin. So let's assume, that the actual axes, okay, right here are in this way, not that the way that they are. So you need a vector which touches the line, and that vector was your RO vector, that's your initial vector, plus you would have your parameter, okay, and then it is scaling the vector which is parallel to the line. That's what you're trying to do. Well, we did that by the method that I just showed you. But another way is that if you want to find this vector in a very fast way, is don't forget that you do have the normals of the actual planes. And if you take the cross product between the normals of normal 1 and normal 2, you know that this cross product is going to give you a vector which is perpendicular to both of them. And so it's going to give you your M. So it's going to give you this. So if you did that, it's going to give you this. Now, is it going to be the same one that we have found through the other method? Not necessarily, but it's going to be some scaled version of it. right? So that's what you would find. So for instance, as you were going through this process, okay, of trying to find what this is, now we have found it, so here it is. So here is, you know, our M vector. Now, if you did the cross product in between, and this is the cross product would be, okay, in between these. So these are my normal vectors. So if I take the cross product in between them, I will find that it's going to be some scalar. So some scalar multiple of this. And now, of course, once you have this, you just need a point. Now, how do you find this point? Well, finding this point, you can just arbitrarily choose one of the variables to be equal to 0, okay? Because you do already have this right here. So you could have said, okay, well, let me set y is equal to 0. Now I can solve for z, because that's going to be just 4z equal to -7. So now I can find out what z would be when y is equal to 0 for this line. And then you can substitute y is equal to 0, and then your z value back into your equation of the line, and then just solve for your x0. That would have been given you an actual point. So that's another way of doing it, right? I don't know which one is faster. Depends how good you are with doing your cross product. So both of them work very well. So again, you would just take the cross product to find your parallel vector to the line. And then you would go back into this method. So you would just isolate, you would find what this is. And now you would find your point by setting one of them. So y is equal to 0 or z is equal to 0. That's the easiest thing to do. You don't have to set them to 0, but it's probably the easiest one. And then just work backwards. All right. So both of them work in either case. So what I would recommend, just to kind of finish this video off and just so that you can get a visual, I'm actually going to plot these two vectors, okay, so that you can see it. And then I'm going to take my m vector, okay, right there. So I'm going to take this vector right there. I'm going to plot it as well so that we have it, okay, on the screen. And then I'm going to shift it over, okay, by this so that you can see it, that it is actually the line that we were looking for. So I'll be right back, okay? I'm going to do that in math3d.org. All right, so I'm back. So this is, it's kind of difficult to be able to see. You can see the two planes. One is dark and then one is also dark green. Okay, so you can, I hope that you can appreciate that. Let me maybe see if I can make this a little bit lighter. It's a little bit lighter, but all right. So this is what you have. And then you have your vector. So I put the vector in there. And it's really hard to see. You can see a little bit of an arrow right there, the blue. Okay, so that's the vector. But let's see if I can, oh, there it is. Okay, so there we go. So you can see that it's right in there. Okay, that's perfect. So that's actually the vector which is parallel to the line. So that vector would span out that line, and notice that it is exactly on that intersection. So that's pretty cool to be able to see that. All right, so that is it. Okay, so now you should know what happens to two planes, how they intersect or they don't, and then how to find the line of intersection if one exists. Thanks for watching. See you in a future video. Bye, everybody.